Good morning, class. The session is being recorded. We are looking at exam 3 review, covers section 3.5, the second part, all the way to section 4.2. Let's recap what we covered already. We need to be comfortable with, differentiation formulas. Logarithmic properties. Started with the implicit differentiation. Couple of examples of that was done here. Same thing here. First, we find an equation of a tangent line using implicit differentiation. Then we find dy dt in the same manner, and understand the moment we see dy dt, that tells us the independent variable is t. Differentiation dealing with logs, natural logs, and logs with a different base using logarithmic properties and differentiation rules. We want to find dy as well as delta y in this example. Dy simply means f prime of x times dx. So first you find f prime of x, then you tag along dx. You plug in x equals 4, dx or delta x equals 0.2, you come up with the answer. Delta y by definition is f of x plus delta x minus f of x, which means f of 4 plus 0.2, f of 4.2 minus f of 4. And as you notice, when we finish the job, the two numbers are fairly close. The reason being, because delta x compared to x is small. That's the idea. We're going to continue on the same thoughts. We're going to use differentials to approximate the cube root of 63.5. Using differentials or linearization, that means that finding a tangent line works the same way as we have seen this before. In order for you to use the differentials, you need to come up with two things: a function, f of x, which will do the job. All you have to do, read the question, cube root of something. So the choice of the function, let f of x be the cube root of x. So that's the first. The next thing is we want to choose a number which is extremely close to 63.5, and we can find its cube root easily without a calculator. We all know that the cube root of 64 is 4, so the choice would be 64. Then we need to calculate delta x or dx. From 64 to 63.5, there is a difference of 0.5, and it's negative. It's important to see how delta x is calculated. And why it's negative 0.5. We know the cube root of 64 to be 4, so we are going to evaluate the cube root of a number which is smaller than 64, so the result will be less than 4. That's why delta x is negative. On the other hand, if you wanted to find the cube root of 65, which is larger than 64, then the result should be larger than 4, and delta x becomes 65 minus 64, which is positive. So the very first thing is to look at f of x plus delta x, which is precisely f of x plus delta y, and it is approximated by f of x plus dy. Therefore, we need to find f prime of x and then tag along dx to give it a name dy. So f of x is cube root of x, or x to the power of 1/3. We know how to differentiate that. 1/3 x to the power of 1/3 minus 1, or x to the power of negative 2/3. So what happens next, we can put the negative 2/3 down and write it as a cube root of x to the power of 2. That's f prime of x. What is dy? You write the same thing times dx. So dy is the same thing times dx. But how do we rewrite this properly? As dx over 3 times cube root of x to the second power. Okay. Now, f of x plus dy, that's what we want. What is f of x? Cube root of x. What is dy? Dx over 3 cube root of x quantity squared. Replace the x with 64. 64. Replace the dx with negative 0.5. That's what we get. And to finish that, obviously this is 4. This is 4. So we have 4 plus negative 0.5, 3 times 4 squared, which is 16. The denominator is 48, and the numerator is negative 0.5. So I put the negative sign in front of a fraction bar, and I'm going to change the 0.5 to 1/2. The reason why, because I want you to notice that 1/2 over 48 means 1 over 96. So the answer is 3 and 95/96. You can use a decimal with a bunch of decimals to do the approximation. And notice the number is very close to 4, because 63.5 is very close to 64. And this approximation is good because delta x is very small compared to the choice of x. Very straightforward, everybody. We want to find an absolute max and mean using the closed interval theorem. The very first thing we need to discuss continuity. Look at the function. This is a polynomial of degree 2 being raised to the power of 3. The result is a polynomial of degree 6. The domain is all real numbers from negative to positive infinity. It's continuous from negative to positive infinity. Therefore, it's continuous from negative 1 to 2. So y is the degree 6, 2 times 3. Now we're going to go with the first step and find f prime of x. So we bring the 3 in front. Same thing, being raised to the power of 2. By the chain rule times the derivative of x squared minus 1, which is 2x. We set that equal to 0. Remember, we want two things. F prime is 0, f prime doesn't exist. F prime itself is a polynomial. By the way, what is the degree of that? 2 times 2, 4, and this has a degree 1, total of 5, degree 5. So it goes down by 1 when you compare it to this one, which means it exists everywhere. We don't have to worry about this part. We set it equal to 0. If you set this equal to 0, what do you get? This part x squared minus 1 is 0. X gives us two answers, positive, negative 1, and this one 2x or just x equal to 0. Therefore, there are three answers. Let's look at the given domain. Negative 1, well, one of the endpoints. Positive 1, is it in between? Yes. 0, is it in between? Yes. So we can use all of it. That means we are going to evaluate this at the endpoints and at all these points. It's really 1 and 0. So let's do that. If we plug in negative 1, we want to see what we get. If we plug in 2, we want to see what we get. Okay. And if we plug in 0, we want to see what we get. We plug in, we evaluate it, and we come up with the answer. For example, if we plug in 0, we get negative 1 cubed, which is negative 1. If plug in 1, 1 minus 1 gives you 0 cubed is 0. If we plug in negative 1 and negative 1 is negative 2, cubed is negative 8. And if we plug in 2, 2 squared is 4, minus 1, 3 cubed is 27. So as it appears, this one is minus 8. Let's just double check that. If we plug in minus 1 squared, no, actually it is 0. Because minus 1 quantity squared is positive on everybody. So it is 0. Therefore, we have the largest number 27. Absolute max equals 27 at this pair, 2, 27. The smallest number is negative 1. Absolute mean equals negative 1 at 0, negative 1. So find the absolute max and mean. That's how we do that. All right. We're looking at a related rate problem. A small rock is dropped into a lake. Circular ripples spread over the surface with the radius of each circle increasing at the rate of 3/2 feet per second. We are interested in finding the rate at which the area is changing at a specific point when the radius is 4 feet. So we are looking at the following shape, a circle with respect to its radius. So here's the information from geometry. A circle has the area pi r squared, a diameter of 2 times r, circumference of 2 pi r. And because we are looking at the radius versus the area, we want a equals pi r squared. So that's the first. We need a piece of information from geometry. A equals pi r squared. We're going to use that. Now let's translate, okay, see what we are interested in. Circular ripples spread over the surface with the radius of each circle increasing at the rate of 3/2 feet per second. That means dr dt is positive 3/2 feet per second. So that's dr dt. What do we want to find? The rate at which the area is changing. So we want the ADT when r is 4 feet. So here's the translation. First, the formula, we need something here. We picked a equals pi r squared. The RDT is 3/2 feet per second. Radius is 4 feet and the ADT is missing. Okay, it's very straightforward. After we translate it symbolically, it becomes very easy to finish the job. We want to find the ADT. So here's A. What is the ADT? Pi times. Now R squared gives us 2R dr dt. I hope everybody remembers that. Let me just write that for you. So this means the A dt is pi, then R squared, 2R. dr dt, or 2 pi R dr dt. All we have to do, replace the given, which means R will be replaced with 4 or 4 feet. dr dt will be replaced with 3/2 or 3/2 feet per second. The reason I mentioned that because the units carry on. So ultimately, the ADT will have the units of the area over the units of time. Okay, it works out that way. This 2 cancels out this 2. We have 3 times 4 times pi, or 12 pi. And we write the units, also approximation with a bunch of decimals. So the answer is 12 pi precisely square feet per second. I suggest you keep it that way, unless they ask you for decimals, and then you carry a lot. This is the precise answer. You want to write that. 12 pi square feet per second, roughly 37.6991 square feet per second. A spherical balloon is deflating, losing 8 cubic centimeters of air per minute. At the moment when the radius is 20 centimeters, we want to see how fast the radius is changing. It's going to decrease, of course. Now, we need to know the formula from geometry. The volume is 4/3 pi r cubed, the volume of a sphere. So we need to know that. So that's a piece of information which is a must. Now, it's deflating or losing 8 cubic centimeters of air per minute. That means what? dV dt is -8. And that's the key. Understanding in this case, we have to put the proper sign. So -8 cubic centimeters per minute. When the radius is 20 centimeters, okay, how fast the radius is decreasing, what is dr dt? So that is the translation, everybody, symbolically. So the volume is 4/3 pi r cubed. dV dt is this number, and because it's losing with the negative sign, -8 cubic centimeters per minute. The radius is 20 centimeters, and we are looking to find the RDT accordingly. So we are going to do the related rate problem, differentiate with respect to t. So we want from this formula to get to dV dt. So we've done this before, so I'm going to remind you how we did that. So we're going to write dV dt is 4/3 pi. Now r cubed gives us 3r squared dr dt, or simply 4 pi r squared dr dt. We had done this a number of times, so I skipped that step, but I wrote it for you here to remind you. 4 pi r squared dr dt, all we have to do, either solve for dr dt or just plug in, instead of dV dt, I'm going to put -8. Don't forget the units, cubic centimeters per minute, because by the time we finish, The units for dV/dt is the units of the volume per unit of time. The units for dr/dt is the unit of the radius, a linear unit over the units of time. So this is -8, this is 4, this is pi, r 20 squared, dr/dt is missing. So what is dr/dt? Divide everything by 4 pi times 20 squared, or 400. 4 pi times 20 squared, or 400. You can do the simplification as follows. Say 8 becomes 2 and 4 goes away. Two changes to 1. 400 to 200. This is the precise answer, 1/200 pi centimeters per minute. Pay attention to the units. The units must always work. You're done. And don't forget the negative sign here. Minus 1/200 pi centimeters per minute. Minus, because it's deflating. Not only the volume is getting smaller, also the radius is getting smaller. And therefore, this is the precise answer. You're done. A rough estimate, you can replace the pi and make sure you write it with a bunch of decimals, okay? This would be the precise answer, and that's good enough. And that's good enough. Let's look at graphing. We want to graph this function using the information from pre-calculus that has been discussed, and we're going to add information from calculus, which means finding intervals of increasing, decreasing, local extrema, inflection point or points, and sketch the graph. Intervals of various concavities. Concave up, concave down. I want to quickly remind you again of what we did in pre-calculus. I'm going to quickly graph this by that method. And then we will look at more details. So number one, if I want to graph this, I need the intercept. So if I set this equal to 0 and I factor the negative x out, so this one is 0, and then x squared minus x minus 1 equal to 0. I want to solve that, and I need to solve this using the quadratic formula. So I'm going to quickly remind you of that. Remember, the quadratic formula is if ax squared plus bx plus c is 0, x is minus b plus minus the square root of b squared minus 4ac over 2a. So going through that process, we get those, and therefore we have the following intercepts. The first one is 0, so 0, 0. 1 plus square root of 5 divided by 2, and 1 minus square root of 5 divided by 2. Square root of 5 class is roughly about 2.2. So what we have here if we were to graph this, the first one is 0, 0. Then 1 plus square root of 5, that means 1 plus 2.2, roughly 3.2 divided by 2 is about 1.6. And the next one, 1 minus square root of 5, that means 1 minus 2.2, that means negative 1.2 divided by 2 is negative 0.6. None of this is to scale. F of x starts with minus x cubed. So what does it mean? N is 3. A sub n is negative 1. Those are the end behaviors. So now if I want to graph this, I bring it down and I hit the x-intercept, and it has to come back up at some point and go down. This is a rough sketch. It's not to scale, it's not precise, but using pre-calculus, we have an idea how the graph looks like. What we are going to do, we want to make sure we're going to make it look better. And that's what's going to happen next by adding things like finding f prime of x and the critical point. So I'm going to erase this and I'm going to go to step 1 here, that is finding relative extrema. Okay, so we are going to find f prime of x, everybody. So let's delete this. F of x, f prime of x is minus 3x squared plus 2x plus 1. We need to set this equal to 0. To do that, it's a good practice not to have a negative here. So we factor out the negative, we do the factoring. I'm assuming we are okay with factoring. If you want, we can write this as minus 3x squared minus 2x minus 1. This is for the sake of factor. Okay, everybody. So setting this equal to 0, x is either 1 or negative 1/3. We do the sign graph. Here's the sign graph. You have a couple of choices. You can find the easiest number in between is 0 and plug in. You can find the number to the left of negative 1/3, plug in either way. To the left of negative 1/3, if you plug in negative 1, what you get is this is negative times negative is positive. This negative in front makes it negative. They alternate. Or pick 0 in between and plug in. 0 makes this one negative times positive is negative. With this negative makes it positive. Anyways, let's put down the arrows. And so what it means, okay, arrow down, arrow up, local minimum at x equals minus 3, up and down, local maximum at 1. Therefore, we plug in negative 1/3 into the original function to find the y coordinate of that pair. We plug in 1 to find the y coordinate of that. I'm assuming everybody can do that. Obviously, if you plug in 1, this becomes negative, this becomes positive, they cancel each other. So you end up with 1. If you plug in negative 1/3, you get negative, and then negative 1/3 to the third, plus negative 1/3 to the second, plus negative 1/3. And that adds up to negative 5/27. You can try it. If you plug in negative 1/3 here, I'm going to leave it for you to show that you do get negative 5/27. Therefore, local max equals 1. Okay, when you plug in at 1, 1. Local mean is equal to, when you plug in negative 1/3, negative 5/27. At negative 1/3 minus 5/27. And again, all you have to do, class, if you plug in negative 1/3, you get minus negative 1/3 cubed plus negative 1/3 squared plus negative 1/3. I'll leave it for you to finish it, negative 5/27, which means we also have the following information. Negative, and negative means what? Decreasing. So decreasing from negative infinity to negative 1/3, union 1 to infinity. Positive means increasing from negative 1/3 to 1. So we got a lot of information here. Okay, so adding to what we have already found, which was what? The intercepts. Let's go to the second derivative to find point of inflection or inflections if we have any. So here's the function. Here's f prime. Okay, let's find f double prime, which makes it negative 6x plus 2. Let's do that. And let's set it equal to 0, and x becomes a positive 1/3. Now we need to do the sine graph on this to see whether we have a concave up or down anywhere, inflection point. Here's what happens. Number line, x, f double prime at 1/3, f double prime is 0. To the left of 1/3, an easy point obviously would be 0. Plug in 0 into f double prime. That gives you positive. And they alternate, or plug in on a 1, and you see it's negative. So what does it mean? Positive means concave up. So it's concave up here from negative infinity to 1/3. Negative means it's concave down from 1/3 to infinity. And because of the change in concavity, we do have an inflection point at x equals 1/3. Now 1/3 has to go into the original function and be evaluated. So concave down, concave up, inflection point at 1/3 and 11/27. So again, you just plug it into this one class, okay? Negative 1/3 cubed. If you were to do that again, I give you the first step and then you can finish that. You plug in 1/3 into this function. So you get negative 1/3 cubed plus 1/3 squared plus 1/3. It gives you 11/27. Now to graph this class, all we have to do, let's summarize what we found. It's helpful. Anytime we have the summary, it's truly helpful. X-intercept at 0, 0. X-intercept at 1 minus square root of 5 over 2, roughly negative 0.620. Another one at 1 plus square root of 5 over 2, about 1.620. The maximum occurs at 1, 1. And we put an arrow there to make sure we understand we don't go beyond that. IP, or the inflection point, at 1/3, 11/27. We change that to a decimal for the sake of locating it, okay? So 0.33, 0.41. That's IP, an inflection point. Minimum occurs at negative 1/3, negative 5/27. Again, we change it to a decimal for the sake of locating it, okay? And because it's a minimum, also we have an arrow. So, and remember the end behavior. So we bring it down, we hit the x-intercept, we hit the minimum, and it bounces back up. We hit the next x-intercept, which happened to be a y-intercept. Goes up, hits the maximum, bounces back down, the x-intercept, and it goes down, and that's your graph. I hope you see that The inflection point C, concave up, then concave down, local max, local mean, intercepts. The function is increasing from here to here, decreasing here, decreasing here, decreasing here. Everything that we discussed is shown in the graph.